Welcome, everybody. So I don't see any... No veo a nadie de fuera. Así que, no sé, podemos darla en español, no sé, como quieran.
Tiene que ser en inglés.
Bueno, por decirme, sí, mejor, sí, por si acaso. Okay, so welcome everybody to the seminar that we have today. It's a really big pleasure to have here Rafael Guzmán. So Rafael did his undergraduate on the Complutense in Madrid. Then he moved to England, where he did a PhD thesis in Durham, under the supervision by John Lucy and Richard Ellis. And then she moved to the States, where he has a first postdoc in the Lick Observatory, working with Sandra Faber and Ku. And then he got a Hubble Fellow at the University of Yale. And since then, he has been in Florida in the last year, where he was first associate professor, and now he's full professor, the equivalent to catedrático here. And from September, he will be a director at the university there. So today he's going to talk about from the blue cloud to the red sequence and how this is related to the formation and evolution of galaxies in the cosmic timescale. Thank you, Rafa.
Pues muchas gracias, Nacho, y buenos días. I have to say that it is a real pleasure to be here talking about science, because I've come here for many times during the last few years and always to sit in various committees. And I have to say that I'm very thankful for this opportunity to let you know about the work that we have been doing at the University of Florida, particularly the work with a couple of graduate students on these issues of investigating galaxy evolution over cosmological timescales, and also to have the opportunity to talk to all of you during the next few weeks about some of these issues. In my talk, I just wanted to divide it roughly into two parts. And the first one, I would like to give an overview of the current picture of galaxy formation and evolution based on the data obtained by huge galaxy surveys, both in the nearby universe and also at intermediate redshifts. And then in the second half, I would like to focus on the approach that we have taken at the University of Florida in order to advance our understanding in some of the outstanding issues that have been presented as a result of this survey work by other teams. And then at the very end, I would like to mention what we see as the future of all the work that we have been doing, not simply by ourselves in the nearby universe, but also by the other surveys at intermediate redshifts. That will imply the access to the new generation of these wide field near-infrared multi-object spectrographs, like EMIR at the GTC and Flamingos 2 in Gemini South. So, ever since Edwin Hubble discovered in 1929 that there were Cepheids in M31, it became apparent that the universe is mainly made up of galaxies, and the basic unit are not stars. Hubble himself attempted the first classification of galaxies based on morphology. This is much better, thanks. And here you see this beautiful mosaic of HST images from the catalog published by Frey and Gunn, in which you have a sense of the variety of morphological properties of galaxies, and also you have a sense of the variety in color. It is now due to the advent of these huge galaxy surveys that we have now provided a complete description of the physical properties of a galaxy population that is truly representative of a particular volume of the universe. And the reference, the starting point, is without any doubt the Sloan Digital Sky Survey that has provided photometric data for over 200 million galaxies, and about 1 million of these galaxies have a spectra that allows the complete characterization of the galaxy properties all the way to redshifts typically of about 0.4. Here you have the image in terms of a cluster of galaxies in the nearby universe as taken from Sloan, and then the typical distribution of the larger scale structure as parameterized by the Sloan survey. And here you have what is becoming one of the main tools to understand how galaxies evolve, which is the color magnitude diagram in an earlier version from the Sloan Digital Sky Survey team, in this case by the work by David Hogg et al. So you have color on the left axis, magnitude, and you see for just a few 100,000 galaxies, nothing compared to the 200 million that they already have, the actual distribution of the galaxies in the nearby universe in this diagram. And what it has become very apparent is that galaxies populate two distinct locus in this diagram. You have, on the one hand, the red sequence of galaxies that are old and quiescent, and then you have the so-called blue cloud of galaxies that are currently star-forming galaxies and much younger on average. It is difficult to see the actual bimodality that exists in color in these plots due to the large concentration of data points. And the better way to do this is simply applying cuts at different magnitudes and study what is the color distribution, as it is shown here, starting from the very bright objects, minus 23 in R, all the way to the very faint objects, minus 16 in R. And as you can see, the brightest objects define a very narrow sequence in color, and they tend to be preferentially red colors. We only start seeing the appearance of the blue cloud, let's say around minus 22. And of course, by minus 20, just about 1 magnitude below the typical L star, you have the clear bimodal distribution between the red sequence and the blue cloud. The reason why it is called the blue cloud, as you can see, is that the width of the distribution is slightly larger. And of course, in the intersection, you have what has now been called the green valley. There's still a lot of discussion going on about the galaxies that reside on the green valley. And it seems, like in the work that Jose Miguel and Cristina have been doing, that AGN appear especially to populate this region in the color magnitude diagram. And as you go to fainter and fainter magnitudes, you can see that the galaxy population in the nearby universe is dominated by the blue galaxies. Now, if we want to statistically characterize the properties of these populations, we have to start with the luminosity functions. And here you have the luminosity function on the left of the red galaxies in red and in the blue galaxies in blue. The luminosity functions are characterized, as you already know, by the characteristic M star or L star value that corresponds to the knee of the Schechter function, the normalization on the y-axis, or phi star, that corresponds to the number density, and then the slope of the faint end. And you already can see what I already was showing you in the diagrams, in the histograms, is that the most of the bright galaxies today in the nearby universe are red, and the vast majority of the low luminosity galaxies in the nearby universe are very blue. Now, these are going to set the reference if we want to establish how galaxies evolve, and we try to measure what is going to be the luminosity function of the galaxy population all the way to the highest redshift possible. But comparing luminosity functions means that we are also affected by the evolution of the stellar populations themselves. So a complementary view to study the evolution of galaxies is to offer the stellar mass function. And this is what it is shown here, again in red for the red galaxies and in blue for the blue galaxies. And this in particular is going to be not affected by the intrinsic properties of the stellar populations, but it will be telling us about how the mass is assembled into galaxies themselves. And as you can see, at least in the nearby universe, the view from the stellar mass or the luminosity functions are very, very similar. Now, I just wanted to review very briefly things that we already knew from the work that had been done in the second half of the 20th century regarding the correlations that exist between in morphology and other physical properties of galaxies. And this is the new version as described by the Sloan Digital Sky Survey. And in this case, we switch to color as the primary property. Here you see the same color magnitude diagram, now in contour plots. There are so many points that it's difficult actually to represent them. Again, the red sequence and the blue cloud over here. And the well-known correlation between color and morphology, it is now described in this plot. If you just look down to this plot on the left-hand side, the late-type galaxies, as described by the Sersic index, are without any doubt belonging and populating the blue cloud, while the early type galaxies dominate the red sequence. And regarding the early result in the 1980s of the correspondence between morphology and environment, here you have the newest version of it. Here you have now galaxies in low density environments and in high density environments. And as you can see from Sloan, the basic result is that if you compare the numbers over here, the late type galaxies in the blue cloud tend to avoid preferentially the high density environments. Again, nothing new here. Is simply we're just showing the state of the art of the results on the characterization of the nearby galaxy population using the Sloan Digital Sky Survey data. And again, the same correspondence between morphology and color and other intrinsic properties of galaxies like age and metallicity. And here you have on the x-axis is age in years, and then on the y-axis you have the metallicity, and this is as a function of mass from less than 10 to the 10 solar masses to above 10 to the 11 solar masses for the blue galaxies, and the same thing for the red galaxies. And again, as it was clearly known, red galaxies appear to be older and have higher metallicity than the corresponding blue galaxies of the similar mass range. But perhaps where most of the effect is clearly seen is in the low mass region, where you can compare the differences in the distribution of the contour plots between these two plots. If you go to the high mass end, you can see that the difference begins to be much less obvious, and we can even say that on average, the galaxies, whether in the blue cloud or in the red sequence, on the massive end, they tend to have a similar distribution in age and metallicity. They tend to be the oldest and the highest, and provide the highest metallicities. New result from Sloan, and this is very interesting, and it's already providing some clues on how galaxies may evolve. Here on the left, we have the average stellar surface density as a function of the stellar mass. And you can see how there is this increasing trend of higher stellar surface density with mass till you reach a certain value somewhere between 10 to the 10 and 10 to the 11 solar masses. What this is telling us is that galaxies are much more efficient in forming stars as they are more massive, till you reach somewhere between 10 to the 10 and 10 to the 11 solar masses, and then there is no such gain in efficiency. And the typical stellar surface density remains constant. Again, pointing out to a different mechanism of formation and or evolution for the most massive galaxies. While below this value, galaxies will remain, in fact, they remain all the way in 10 to the 7 solar masses in our latest results, following the same trend already described here by Sloan. In a completely different way of looking at the properties of the galaxies nearby is looking at the current star formation. And here you have a parameter that can be used to parameterize this star formation activity. It's called the specific star formation rate. And what this gives us is the characteristic time scale in which a galaxy today can form all its stars at the current star formation. For example, a galaxy about 10 to the 9 solar masses that is currently forming stars in the nearby universe is doing so at a rate that maybe in about 1 or 2 gigayears has actually formed all the stars that already are there, right? That's what this parameter is telling us. So most of the star formation activity, the most vigorous star formation occurs in low mass galaxies today. And then the trend seems to suffer an abrupt change towards the high mass end. Again, pointing out towards the existence of a critical stellar mass value that has been identified around 3 times 10 to the 10 solar masses, and that we believe is giving some information, giving some clues that are essential in order to understand how galaxies grow their stellar mass, how galaxies form their stars, and then they evolve between the blue sequence and the blue cloud and the red sequence. If we now go to the intermediate redshifts, the equivalent efforts to the Sloan Digital Sky Survey are being provided by a wide variety of teams. In particular, I would like to highlight the work by the DEEP team at Keck and the VVDS team at VLT. They already have close actually to 70,000 galaxy spectra in the range between redshift 0.4 and 1.3. Again, just extending the same characterization of statistically representative samples of galaxies now into the last 9 gigayears. And here you have this beautiful view of the Hubble Ultra Deep Field, just to illustrate the typical galaxy in the nearby universe, a disk, a spiral galaxy, compared to the typical galaxy at higher redshifts, these very small, very blue, and intrinsically very luminous objects. Now, what have we learned about the comparison of the color magnitude diagram at different redshifts? And this is the work by Bell et al. Here you have again the color magnitude diagram. In this case, the reference in the low redshift bin, and how things change if you go all the way to about redshift of 1. First thing, you can still see what it is, the solid line that reflects the location of the red sequence. And the dashed line corresponds to the division between red sequence and blue cloud. Over here, the dotted line corresponds to our selection effects associated to the Malmquist bias and to the K correction. You definitely see quite a few red galaxies, bright red galaxies. However, the most important change is seen in the blue cloud. There are many more blue galaxies that are very luminous than the corresponding red galaxies at redshift of 1. The best way to parameterize this is going back to the luminosity functions. And here you see the evolution of the normalization of the luminosity function, phi star, as a function of redshift. And it is done for several morphological types. The red galaxies will be type 1, 2, and 3, and the blue galaxies part of 3 and 4. The most important result is that as you go back in time, all the way to redshift about 1, 1.3, the number density of the red galaxies tend to decrease. The number density of the very blue late-type galaxies increase substantially. These galaxies are forming stars vigorously, and as a result, they will increase the overall star formation rate density of the universe at these epochs. And here you have the very well-known by now evolution of the star formation rate density of the universe with redshift. This is taken with the latest results from the GALEX work. The difference between these data points and these bands is simply the correction due to extinction. The overall behavior is the same, is that the universe was more actively forming stars in the past, by a factor of 10 all the way to redshift 1, and most of this activity occurs in normal disk galaxies. However, beyond redshift 1, we still maintain a very high level of activity of star formation activity in the universe, and most of these galaxies are these late type, very blue, very luminous objects. So we're moving now into identifying the redshift of 1 as a transition epoch in the history of the universe. And it is very nicely illustrated in this mosaic of the characteristic galaxy at a given luminosity at different redshifts. So over here you have redshift for 0.19 all the way to 3.6. And over here you have galaxies of different luminosity. So this is basically the color magnitude diagram at a particular redshift, right? And all galaxies here will have approximately the same luminosity. So what you can see already here is that by redshift of 1 over here, you see the red sequence very well formed, right? However, by redshift of 1.5, there's no red sequence. There are no red galaxies. So the appearance of the red sequence occurs somewhere between redshift of 1.5 and 1. Most of the galaxies here are very blue, very luminous, and very compact in size. And that's why we call them Luminous Compact Blue Galaxies. And in the second part of the talk, I will focus on what we are learning about these galaxies, particularly regarding the evolution into the red sequence. Because barring the existence of some unknown and heavily obscured galaxy population at high redshift that we have not found yet, it is clear that the progenitors of the massive early type galaxies here have to be in this population at even higher redshifts. So, here is the situation with the color magnitude diagram for galaxies in the slow version in 2003. This is, for comparison, another famous color magnitude diagram that the people here, especially Karma, may know very well. This is for stars. And one of the greatest successes of astronomy in the second half of the 20th century was to be able to break the code on how stars actually evolve in the CMD. This is our goal now. We are trying to understand how galaxies evolve in the color magnitude diagram and what are the physical processes that determine that evolution. What are the new clues that we have? It's not simply the clear bimodality in color that we already saw at the very beginning, but also the presence of this critical mass value at about 3×10 to the 10 solar masses. Why can't we have blue galaxies that will be this luminous, right? And if we don't have galaxies here, how are we forming these very massive red galaxies? There must be two main physical processes that are getting most of the attention of the theorists at the moment. One is the quenching mechanism. There must be a way in which a star formation has to be halted around this critical mass value, and it will prevent from continuing forming stars in this part of the diagram. The second mechanism is merging, because the only way in which you may be able to form galaxies here, again, if we're seeing all galaxies there are, is by merging either of these galaxies or these galaxies over here. These are the two main mechanisms, mergers and star formation quenching. And in the star formation quenching, there have been three different approaches that are being considered theoretically. How can we prevent stars from continuing being formed? The first mechanism is the critical mass halo approach. Basically, as you build larger and larger galaxies, more and more massive galaxies, the virial theorem will imply a higher velocity. The higher velocity will translate into a higher temperature for the gas that will prevent the cooling of the gas and the continued formation of stars. And according to the latest round of models, this value, the critical dark matter halo, occurs around 10 to the 12 solar masses. The second mechanism is AGN feedback. Also, AGN will provide a heating mechanism of the gas in the galaxy, and therefore will prevent the cooling and the fragmentation, and therefore the continuation of star formation. And finally, we have the feedback associated to the supernova associated to the star-forming regions in some of these galaxies that will also prevent the continuation of formation of stars. So, the two basic approaches in this very, very naive, simplistic picture of galaxy formation that refers to first the formation of massive galaxies start with the hierarchical collapse of the dark matter halos, the hierarchical clustering of the dark matter halos, with the dissipational collapse of the baryons in the centers. And you will have a continuous tree of mergers till eventually you end up with a massive galaxy today, where star formation has to be prevented by any of the three quenching mechanisms that I just mentioned. In this case, how would galaxy move? What would be the evolutionary tracks in the color magnitude diagram? Well, galaxies would start on the low luminosity end of the blue cloud. They will move along the cloud due to the continuous transformation of gas into stars, and also due to wet mergers with, between galaxies with a substantial amount of gas, till they reach the quenching band. And at that point, the star formation will stop, and the galaxies will fade and redden into the red sequence. And then you will need a substantial amount of dry merging between already evolved galaxies in order to create the massive high luminosity end of the red sequence. Yes? Oh, sorry. They will. They will. And in fact, that's what I will show in the next slide. I was simply just focusing on the evolution of the most massive galaxies. You're completely right. But the second scenario is the one that comes now. I would like simply to say that a particularly interesting population then would be precisely the blue galaxies that reside at the luminous end of the blue sequence, because it would allow us to study the mechanisms of the quenching of the star formation, and then what will happen or how they will evolve into the red sequence. The second approach is precisely what may affect to the low-mass galaxies. That will also start with the same hierarchical clustering of dark matter halos, but in some cases, some of these galaxies will end up as satellites of a much larger dark matter halo that, because of the virial effect, will prevent the continuation of stars. And these galaxies will either reside as satellites of a massive galaxy today or as lower mass galaxies in clusters of galaxies. And in this case, the evolution will be what you were just suggesting. So we will have blue galaxies that may grow along the blue cloud, again due to the transformation of gas into stars or wet mergers, till they fall into these larger halos, and then they will redden to create the population of low-mass red galaxies. So in this case, another interesting population would be precisely the low-mass early-type galaxies or red galaxies. And this is the approach that we have taken in Florida. We have focused on studying galaxies that are in the low mass range in the red sequence in the nearby universe, and this is taking advantage of an HST treasury program with the Advanced Camera Survey of the Coma cluster. This is to a large extent the results from Anna Matkovic's thesis. She finished last year, is working in Space Telescope now with Harry Ferguson. And then the second approach is going precisely to the other extreme, which would be to focus on the massive galaxies in the blue cloud, also in the nearby universe, selected from Sloan. And these are the results from Jorge Pérez Gallego's thesis, also at UF, that he finished this May, and will be visiting Complutense to work with Jesus Gallego this fall. So we're going to be focusing on these two. I will not mention much about the first part. That will be a completely different talk. I'm going to be focusing on the results that we have obtained in the study of the second population. And of course, our goal eventually will be to extend the same type of galaxy surveys that have been carried out in the nearby universe with the Sloan Digital Sky Survey, and at intermediate redshifts with surveys like DEEP and BVDS, but this time beyond redshift of 1. And by that, we will need EMIR at the GTC and Flamingos 2 in Gemini South. I could not resist to show you at least the beauty of our HST data. This is the image of the Coma cluster, NGC 4889 and 4874. Almost every single dot of light that you see here is a galaxy. I did my thesis in the Coma cluster studying this type of galaxies. We thought they were about the state of the art of what we could do in the 1990s. Now we're focusing on this type of galaxies. Anyway, so we will now move into the second part of the talk just to show you the results from our study of these galaxies that we call Luminous Compact Blue Galaxies. We already know that these are the dominant L-star population of redshifts larger than 1. They contribute significantly to this increased activity of the universe in terms of the star formation. And they have also masses near the critical mass, around 10 to the 10 solar masses. That's why these galaxies have become a very nice laboratory to explore this type of phenomenal physical processes regarding quenching and evolution into the red sequence. What are the fundamental questions? These are starburst galaxies. So the first question is, what is triggering the burst? Also, what is quenching the star formation? Because they are close to the critical mass. So can we discriminate between some of the three scenarios that I just showed you earlier? And of course, eventually, what will be the most likely evolutionary path into the red sequence? Just to highlight again, here is a typical luminous blue compact galaxy of redshift 1.1. This is from the work by Kano Esquetale in Lake Observatory. And we would like to discriminate between the following two scenarios. Whether this galaxy of redshift 1.1, 9 gigayears ago, will actually become this dwarf elliptical, something like NGC 205, in a satellite of a much more massive galaxy, or whether it will end up being the spheroidal component of a much larger galaxy that will grow inside out. Right. Okay, what is what we need? And this is what we're focusing right now. Well, we try to understand the process of star formation and mass assembly. In that case, we have conducted a multi-wavelength extensive study of a subset of these LCBGs selected from Sloan in a way that I will just mention in a minute. We would like all the information about the star formation rates. For example, we would like to have the far UV fluxes from galaxies and also the H-alpha maps, in this case obtained with the three-dimensional spectroscopy. But also we would like to know how much more gas we have as an immediate reservoir for star formation, meaning the molecular gas that these objects have, in this case using CO as a tracer with overall, and eventually what is the total gas in the galaxy that may be used to be transforming the stars using VLA or the GMRT in India. But then we also want detailed information on the kinematics to be able to tell us about the masses of these galaxies and also the assembly of the masses if we distinguish any features of major or minor mergers that sometimes are difficult from the morphology analysis alone. And here you have the velocity maps as derived from H-alpha, but also as derived from H1, because these maps will give us a much better handle on what is the actual halo masses, since they will extend much larger than the actual extension of the ionized gas in these galaxies. So we selected our galaxies from Sloan, applying a cut in 3 observational parameters: luminosity, color, and surface brightness. These galaxies are brighter than -18.5, and the only reason why we did this is because these galaxies will be seen all the way to redshift of 1 in the typical HST image, at the typical depth of an HST image, for example, in the Cosmos survey. Then here you have the surface brightness versus color. These are the 2 cutoffs that correspond to these 2 values. We're selecting galaxies here. On the one hand, we have a cutoff in color to select the bluest of the blue sequence in this color bimodality that you can also see here with surface brightness, and also the highest surface brightness or the most compact galaxies, because these objects will be seen all the way to higher redshifts due to the effect of cosmological dimming that will make lower surface brightness galaxies disappear from your surveys. So this is very much the criteria that we gave. We focused on 200 megaparsecs in the Sloan survey. There are about 2,400 from which we're deriving the statistical properties, but we are focusing explicitly on about 24 galaxies that encompass the whole range in the parameter space in order to provide this detailed multi-wavelength 3-dimensional study. And just to give you an idea, in the color stellar mass diagram, our points are the solid points here. Again, they tend to be on the bluest part and on the high mass end of the blue sequence. On the specific star formation rate versus luminosity, they are right on the limit of the most extreme galaxies, those that have the highest specific star formation rates. This we never, yes. Yes, that's right. All of them, the 2,400 comes from Sloan, but we will focus 24 for the 3-dimensional spectroscopy at different wavelengths. That's right. Only with a spectra from the 1 million. No, that's right. It's the spectroscopic catalog of 1 million galaxies. That's right. That's right. But already it's telling you that these objects are very rare nearby. There are only 2,000 within the volume of 200 megaparsecs. And this is how they look like. We never selected by morphology. Then we went to the Sloan, looked at the images, and here you see them. And you can see evidence for distortion in their morphologies in quite a few cases. In some others, they look like normal small spiral disks. Here you have the Sloan spectra, integrated spectra, and again, a wide variety of properties. You have spectra dominated by continuum here and here, characteristic of the spiral galaxies, but also you have spectra dominated by emission lines, very much characteristic of H2 galaxies. Okay. Now, what have we learned? Let's go to the first question. what are the virial halo masses of these objects, and see whether indeed they will fall below the 10 to the 12 solar masses critical value already predicted by some models. In our case, we are using the H1 halo masses as a surrogate of the actual dark matter masses, right? Here you have the distribution of the halo masses as derived from Arecibo data for about 150 of these objects. And as you can see, this is the 10 to the 12 solar mass. And clearly, the vast majority of our galaxies fall below that value, consistent at least with the idea that beyond this value, it is very difficult due to virial heating to continue forming stars. The gas depletion timescales are telling us something about how long the galaxies can maintain the current physical state of forming stars at the current star formation rate. And of course, it's a combination of how much gas you have and how quickly you are consuming that gas. And over here you see the characteristic gas depletion timescales. And about 80% of the LCBGs will consume all the gas that they have in about 3 gigayears. And after that, they will fade and redden. So within 6 gigayears, they will become typical evolved quiescent objects in the red sequence. Now, if we go to the detail of the kinematics, here you have 3 examples that characterize the division in the velocity maps that we have done in Jorge's thesis. Over here, you have a rotating disk. Look at the morphology, how distorted it is, how different from the typical spiral galaxy. However, if you look at the velocity map and then the velocity dispersion map, this is the characteristic velocity map and velocity dispersion map of a rotating disk. Here you have the gradient in velocity, roughly about 200 kilometers per second peak to peak. 400 peak to peak. And then here you have the highest velocity dispersion that coincides with the zero velocity line, as it would be expected in a virialized rotating disk. Right. So about a third of our objects do show characteristics in the velocity analysis of normal rotating disks, but about 2/3 show differences. About 1/3, we call them perturbed rotators, because even though they show the clear gradient of a rotation, there is no correspondence between the zero velocity line with the value of high velocity dispersion. And then the final third or so corresponds to objects with complex kinematic, in which we are not able to distinguish any clear rotation pattern or any association with any clear peak in the velocity dispersion velocity field. Now, just to give you some warning on how difficult this analysis is. So I just show you the typical object for a rotating disk case. This is Markarian 297. And here you have again the rotation. This is in fact a clear example, the only clear example that we have in our sample of major mergers. What you are seeing here, in fact, is the collision between 2 galaxies of roughly equal masses. And you can see this much better and understand what's going on in the velocity map by looking at the H1 distribution. So here you have the contours correspond to the actual optical image of this galaxy. And then in grayscale, you have the distribution of the H1 gas. You're having the collision between an H-on spiral galaxy here with an almost face-on galaxy that is over there. And here you see the rotation clearly along this direction and then the face-on galaxy over here. And then you have something else going on here on the tail of this H1 extended distribution that has no clear correspondence with any optical counterpart. Again, this is to illustrate how important it is to be able to combine the information at several wavelengths. Because in fact, without this, we would have interpreted wrongly that this was a rotating disk in this direction, where you have the maximum gradient. And that is not the case, as you can see. But this was the only clear example of a major merger that we have in our sample of LCBGs. Much more common were the presence of kinematically decoupled components along the lines of what you see here in these red circles. These are components that have a velocity difference typically larger than 100 kilometers per second. In this case, it's as high as 300 kilometers per second. We're looking at objects that most likely are falling towards the galaxy at a very high speed. And if you remove these components, you recover a very, very nice rotation disk underneath. Now, we have about 20-25% of galaxies in our sample that show these kinematic components. In this case, we would like to go a step forward and bring some light into the question of whether some of this could be identified with impactors, minor mergers that may be responsible for the star-forming event that we're seeing. In this case, we have focused our discussion in this component in Markarian 325. Here you have in contours the same velocity field that you saw here, and then in grayscale you have the metallicity map for Markarian 325. And you can see clearly that the component that has been kinematically identified also shows a difference in metallicity as compared to the rest of the galaxy itself. The same difference appears also in the equivalent widths of the absorption lines, telling us something about maybe the different nature of this object. Now, this also could be an H2 region within the galaxy. So if we now go and plot this luminosity of H beta versus velocity dispersion, this is the relationship that is followed typically by H2 regions. Indeed, you can see that our impactor, which is here in red, follows the same relationship, but is simply much larger in size and in velocity dispersion than any known H2 region. It is much more consistent with being what is called an H2 galaxy itself. All this points out towards evidence identifying this component as the impactor of the galaxy. Again, evidence for a minor merger that may have triggered the burst. And the same type of analysis we're doing now, we're currently working on it for the second paper, on these other kinematically decoupled components. Then we move into the presence of supernova-driven winds. It is a difficult subject because we identify them spectroscopically, but not especially. It's not like the previous components that were decoupled, both in terms of space and in spatial and spectral properties. Here, in one single fiber, in different locations of the galaxy, we actually see evidence for kinematically decoupled components. And this could be the typical profile that you would see in a supernova bubble that is actually moving, and you see one region moving towards you and the other one moving away from you, and that's basically what you will see in these profiles. But we need to do much more analysis in order to be able to discriminate on what level we can say these are supernova bubbles, and instead of simply being much smaller foreign objects or different stellar systems that we cannot resolve. Our resolution is typically 1 kiloparsec. That's the size of our fibers at the redshift of these galaxies. And finally, the role of AGN. How important this may be, AGN, as a heating mechanism to prevent continuous star formation. Well, we only have one example in our sample of LCBGs that shows the clear signatures of AGN, both in the width of the velocity, in the width of the emission lines. It's typically about 250 kilometers per second. It's a low luminosity AGN. Remember, this is just one fiber within the galaxy. And then in the line emission ratios that clearly identify this component as having the properties characteristic of an active galactic nuclei, instead of the star-forming sequence clearly defined over here in this diagram. So the summary is that what we have found from our analysis of the nearby LCBGs, in terms of the morphology and the kinematics, we don't see clear evidence of major mergers, one-to-one mergers in the collisions of these galaxies, but we do see evidence for minor mergers and strong interactions that may be triggering the starburst. And the quintessential example is Markarian 3 to 5. Now, regarding the gas depletion time scales, they will consume all the gas, and they have plenty of gas, but they are transforming it at such a high pace into stars that by 3 gigayears, they will have already extinguished all the gas, and then after that, in only 3 more gigayears, they would look very much like red galaxies in the red sequence. And then, regarding the masses and kinematics, perhaps one of the most intriguing results is that we do not see any objects that may have halo masses above the critical value predicted by some models of 10 to the 12 solar masses. For those objects that clearly rotate, the characteristic rotation velocity is of the order of 50 to 150, one all the way to 200 kilometers per second. And the dynamical masses that we derive, they are of the order of 10 to the 9 to 3 10 to the 10 solar masses. And finally, from the actual detailed analysis of the velocity maps and the velocity dispersion maps, we conclude that a substantial fraction of these objects are non-relaxed, with about 60% showing kinematic subcomponents that could be either consistent with minor mergers or supernova-driven winds. And finally, we find very little evidence for a strong effect on AGN as the main quenching mechanism in this particular sample. Okay, just a note of caution when we try to apply the same type of analysis to higher redshifts. And I would like to show you the results obtained with Giraffe of galaxies at redshift less than 1. So here you have the layout of the IFU over the image of the galaxy. And here you have, most importantly, the pixel size, the spaxel size, basically your resolution element, with a color code for the signal to noise. We had typically about 100 to 200 spaxels per galaxy in our analysis, with signal to noise going up from over 150 to more than 15, because below 15 we didn't feel confidence about our own measurements. The signal to noise ratio in this particular case goes from 4.7, and that's the highest, to 3.3. And from this information, by repixelation and interpolation, you then derive this velocity map and this velocity dispersion map. Again, of course, this is one of the worst cases. You have a much better case here in which you go all the way to 32 in signal to noise for the central spaxel, and then all the way to about 4 in signal to noise for the rest. All to say, it's already very difficult to adequately interpret the velocity maps and kinematics of these heavily distorted objects in the nearby universe with all the wealth of information that we have. Let's be sure that we don't overinterpret the results of our velocity maps at higher redshifts. What is the best way that we can do this? We can do simulations of our galaxies and how they will be seen using the next generation of IFUs in the near infrared and with the 10-meter class telescopes. For example, here you have a prototypical galaxy, Markarian 538 in this case, with 3 very large knots of star formation. This is the star formation map, or the H-alpha flux map. And here you have the velocity map. These are actual data for one of our galaxies. And we have been able to simulate how this galaxy would be seen in 4 hours exposures with Frida at the GTC. And you can see you can recover even the presence of the 3 knots of star formation. And also you can recover most of the bulk of the velocity rotation field. If you go all the way to redshift 2.5, you're losing completely most of the information in this galaxy. I doubt that we can do much about these galaxies, and we can still go perhaps to the highest luminosity ones, but about these galaxies around L star, galaxies at redshift 2.5 with 10-meter class telescopes. However, we will be able to do plenty with the new generation of giant telescopes, the 30 or 40 meter class telescopes. And these are the results of the simulation that we published in the science reference document for the TMT, the 30 meter telescope, published in 2007. And again, you can see how beautifully you can recover both the H-alpha flux and the velocity. If we cannot do the full three-dimensional analysis of these objects, we can still do the analysis of the integrated properties. And this is the basis of the survey that we proposed to do about 12 years ago when we first proposed to build a mirror for the GTC. Here you have the extended growth strip, the mirror field of view. This is the simulations of our galaxies as they would be seen through a mirror at the GTC with 4-hour exposures, and how well we can recover with adequate signal to noise the H-alpha emission line. And that's the basis for the approach that we are now taking for the immediate future, which is to extend the work by DEEP and VVDS at intermediate redshifts all the way to galaxies beyond redshift of 1. And we can do this because we do have privileged access to the 2 state-of-the-art instruments that are currently being finished. On the one hand, we have the Flamingos 2 instrument in the Gemini South. And this is the work that we are now starting in Florida. We have about 7 nights. We would like to observe about 600 galaxies. And then, when a mirror is ready, we would like to use about 30 nights that we already have guarantee time in GTC in order to provide a comprehensive study of another 2,000 galaxies. 3,000 galaxies may not look that much at this redshift range. But just to put it into perspective, it could be 20 times larger, the sample, than any observation that the complete set of observations that have been done so far with these type of H-alpha observations of this distant galaxy population. And just to remind you on the main science goals for GOYA, our survey with GTC and EMIR, we would like to focus on the characterizing the star-forming galaxy population of redshift larger than 1, based on our understanding of how much we can interpret about the star formation from the H-alpha fluxes and the kinematics from the H-alpha velocity widths, but also considering metallicity and extinction. Most importantly, we would like to focus on the study of the early type massive galaxies in the redshift range between 1 and 2, which is the redshift range of the creation of the red sequence. And then also characterize the census of the supermassive black hole at higher redshifts by measuring the velocity widths on the H-alpha and H-beta emissions, and eventually search for the most distant galaxies so far, the Lambda alpha galaxies at redshifts beyond 6. And if any of you is more interested in learning more about the GOYA, I just finished by giving you our website where you can find much more information. Thanks very much.
Time for questions.
Could you say something on the metallicity and age of the luminous blue galaxies? You've mentioned a little about
yes.
These factors and the difference of metallicity, but just
yes.
to have a global idea.
Yes. In fact, this is the work that I hopefully will be able to complete by next year. Since we have the complete spectral map in 2D, we're now able to measure at each position in the galaxy age and metallicities for both the underlying population and the young population associated to the current burst. We're doing this using emission lines for the burst and using absorption lines for the underlying population. And what we are seeing so far, and this is again very preliminary, is that the metallicity of these objects tend to be typically about 0.7 for the burst and comparable for the underlying population. And the ages of the underlying population are at least 3 gigayears old, if not older, while the ages for the bursts can vary depending on the star-forming regions, anywhere between a few 100 million years and about 1 billion years. But again, we would like to produce the same detailed maps of ages and metallicities for both components in the near future, similar to the results that I provided here for kinematics. Yeah,
it's larger, it's smaller?
It's larger. It's larger, which actually was a little bit surprising. But then when we put the impactor into the luminosity-metallicity relationship, it actually fit within the scatter, the luminosity-metallicity relationship of typical H2 and irregular galaxies. But we were a little bit surprised that it would be higher than the remaining.
When you show the evolution of the morphology of galaxies as function of redshift, basically you see that you don't have bright red galaxies beyond redshift of 1 or less. Does this observation contradict with the fact that when you characterize the stellar populations of elliptical galaxies with the stellar population synthesis methods, you find that they are old?
Yes.
I mean, how do you reconcile these two observations?
And this is the obvious conundrum, because we have to distinguish on the age of the first stars of the galaxy, right, with the time of assembly of the galaxy. And the two things are different. So you may have stars that can be very old and eventually will be the cores of elliptical galaxies. But the elliptical galaxy itself will not be assembled till a later epoch. Right?
More questions?
Just a clarification. When you say that the metallicity in the factor is enhanced, are you referring to metal phase metallicity or stellar metallicity?
It was the gas, because
the gas,
we measured
no?
exactly from the gas. That's right. So,
you cannot say anything about the stellar metallicity in that.
no, we have not done. It is very difficult sometimes to do because of the very very large contribution of the emission lines. That's it.
Rafa, maybe I missed it, but could you comment on how did you select your subsample of 24 galaxies? I mean, they're just a random sample from your 2400 sample, or
Yes.
there's...
I forgot to add one for that question, one slide. But basically what we did, if I can go back. What we did is we only had 24. We tried our very best not to look at them, not to bias. Some of them were really nice, and in fact some of them we thought that they had companions. But we decided not to look at them, just go back to their position in the two main plots, which is the surface brightness color and the color luminosity. And the only thing that we did is to ensure that these 24 would encompass the whole range of properties in this three-dimensional parameter space. Even though, by its very nature, we biased our sample to the most extreme because we wanted to encompass the whole range, but the most extreme, there are very few. Most of them are close to the, as you can see here, to the cutoff lines.
Just because, I mean, as you know, Markarian 297 is usually classified as a regular BCD dwarf galaxy, not luminous.
That's right. That's right.
Any further question? Well, then I have the privilege to do the last one. So you said in one of your intermediate slides that you would like to know whether these blue galaxies will finish like a satellite or in the center of the Milky Way, for example. What did you find in relation to the metallicities and things like that? What is the most common scenario? Have you got any idea?
Okay, so I mean, as many other cases in astronomy or in science in general, the results are never black and white. And from the preliminary analysis that we have done, and again, we have not done the detailed evolution spaxel by spaxel of the entire galaxy over 3-4 gigayears, considering all the gas depletion timescales, then the typical evolutionary population synthesis models. We have not done that yet, but we will do it. But on average, just using the average properties, we find that about 60% of the galaxies in the samples that we had masses that would be too small at least to provide the seed for the major bulge of a massive grand design spiral galaxy as we know it today. However, the remaining, we saw objects that could have close to 10 to the 510 to the 10 solar masses, and that they are roughly rotating, and given the time for evolution between redshift 1 and now, and the huge amount of gas that they still have, it is likely that they could grow the disk inside out. So no final answer there, but we cannot discard any mechanism except that perhaps a certain majority of these objects would fall into the lower mass category.
I was just considering the nearby ones. So how the nearby ones will finish? Will finish like the satellites, or? So I was not asking
That's
the
right.
hierarchy, but the nearby.
Sorry, the result applies to the nearbys, and I just extrapolated to the distant universe.
Okay.
That's right.
Okay, thank you. So no, you don't have that privilege. Sorry. Okay, wait. In any case, just let me say that Rafa will be here the next 2 months, no?
Yeah, that's right.
So we will have plenty of time for talking with him.
Just a general a comment to, well, to see if you would comment on the idea that the cutoff that one infers from the color magnitude diagram, from the mass color diagram, the higher mass cutoff in the blue cloud, which has been used repeatedly to try to infer what is the physics that truncates star formation. Shouldn't this limit be time dependent, in the sense that 8 gigayears ago it had to be somewhere else, and that downsizing in a way means that this limit has been moving back, and therefore all the tracks that we are painting as favorite color paints on that diagram are too much based on the zero redshift color magnitude diagram rather than on the color magnitude diagram at the time when these galaxies were assembled.
Yes, Mark. Again, I mean, your point is well taken. I believe that we can use this diagram to illustrate further. So you can see here, again, that comparing the color magnitude diagram at redshift 1 to the one at redshift 0.3, what you have is a lot of these blue galaxies that are also very luminous, right? And that they do not appear here. They should be over here, as you can see, right? And that's exactly what you were referring to. And you're right. But what it was a little bit surprising is that when you go and translate what you are observing in terms of luminosity variables into mass variables, you rarely, or within the errors, you can go much further than 10 to the 10 solar, a few times 10 to the 10 solar masses in the blue population. So what you see mostly is also evolution in the stellar populations. In addition, and you're right, to the fact that as it has been known, the downsizing scenario, as you go back in redshift, this phenomenon of vigorously star formation will occur more and more often in more massive systems. But you don't go much further above a few times 10 to the 10 solar masses in the blue cloud. There are a few galaxies, of course, as you know very well, in which there have been measurements of 10 to the 11